Hello, good morning. This is Miguel Azanha from University of Minho, together with Fragolis Canavares from ARUP, ready to start our presentation about the RILEM TC 287 CCS on early age and long-term crack width analysis in reinforced concrete structures. We are really thankful for Professor John Forth for having invited us to participate in this course, and we hope that our presentation will provide a clear enough insight into our RILEM TC and hopefully even gather further participation in it, but at the same time give you all a perception of the challenges that we are perceiving nowadays on these matters and how we are trying to contribute to a better knowledge on this field of science, but technical field as well. We start by providing a little bit of background on ourselves, and I start by mentioning myself, Miguel Azanha, as currently an assistant professor at the University of Minho in Portugal in the Department of Civil Engineering. I have a career I would consider relatively unique because I was a designer in the first years of my career. I was not considering to become an academic. So on the right-hand side, you see me roughly speaking 20 years ago. And then I shifted to academia and I got my PhD in 2009, in which I had the pleasure of having a participation with the University of Tokyo. And the subject was numerical simulation of structural behavior of concrete since its early ages. In the meantime, in my postdoctoral period, I had the pleasure of starting some initiatives that were really impactful, at least on me. And one of them was to start the Cost Action TU 1404, which is a figure of financing that allows researchers and practitioners to travel throughout Europe for several meetings on a common topic. And this common topic was going towards the next generation of standards for service life of cement-based materials and structures. This was active between 2014 and 2018. It's already finished, but it's got quite an impact and on the fact that we were able to do a lot of initiatives in the RILEM TC 254 CMS, which is in the line in the bottom on thermal cracking of massive concrete structures, and then on the TC that we are sharing now, the 287 CCS early age and long-term crack width analysis in RC structures. In the meantime, I also have other activities that I think are worth mentioning. I'm the director of the European Master in Building Information Modeling, BMA+. This is funded by the European Commission as well, and it's still going with funded period. And it again shows my connection to the industry, which I try to keep very much alive, and also a connection to the world of cracking in a different setting than reinforced concrete, which is the last line on my slide, which is I am the deputy coordinator of the Sustainable Building Lime Applications via Circular Economy and Biomimetic Approaches. It's a Marie Curie ITN network that has hired 15 PhD students all working together. And of course, I'm there for the cracking, amongst other things. So Fragolis, I would now invite you to present yourself on this next slide, please.
Thanks, Miguel. So hello, everybody. Welcome to this course, and thanks to the organizers for inviting us to open the course. I'm Fragolis Canavares. I'm a concrete materials specialist at ARUP. I provide expert concrete advice related to concrete cracking, durability, technology, low carbon concrete, and all sorts of peculiar problems with concrete on global scale. Initially, my training was in civil and structural engineering, obtained that from Liverpool, University of Liverpool, 2013. And then I went on to pursue a PhD in concrete technology, cracking risk, slag-based concrete and supplementary cementitious materials, which was awarded in 2017. This is a photo of me on the right from 2016 or 17. Sorry, Miguel, this is not 20 years ago, but still. And during my years in Queen's University Belfast as a PhD researcher, I had the opportunity to actually be introduced to RILEM and meet all these great people that RILEM is about. And one of them was Miguel Azanha, with whom we collaborate And since then, we are continuing to collaborate and merge, let's say, the academic and industry worlds towards a better understanding of crack control and cracking mechanisms. Hence, we are coordinating this RILEM Technical Committee on Early Age and Long-Term Crack Width Analysis in concrete structures. On top of that, I have been significantly involved with the development of with updates actually on a very well-known guidance document on crack control in concrete, Series 766, successor of Series 660, for which my team was taking care of the technical updates and editing of the document. I'm also the convener of Tech Task Group 4.6, where we're looking at constitutive laws for concrete with supplementary cementitious materials. This is very important because the constitutive models we use in our calculations need to encompass the peculiarities associated with alternating the behavior of concrete with supplementary cementitious materials, as this affects the crack control calculations that we are doing. And I'm generally coordinating most of the concrete materials related research within ARUP, and I'm a member of several other RILEM technical committees and standard drafting committees. So thanks very much, Miguel. Over to you to continue with the presentation. Thank you.
Okay, thank you, Fragolis. And it's never too much to stress the fact that it's a pleasure to jointly lead the TC with you in this very interesting connection between academia and the industry which you are representing now. So this is something we are finding to be very fruitful in the way we can approach the leadership of the TC. So to put a little bit of scope on the presentation, we all know that the stresses in reinforced concrete structures are inevitably affecting how cracking is happening in reinforced concrete structures, and this is a complex thing. So we have many factors contributing to the way concrete will crack, with some of them being shown in this slide. So we start with the early age thermal effects. So we all know that the cement will have an exothermal hydration reaction, and it will generate an increase in temperatures within concrete. These temperatures will generate expansion, and this expansion will cause stresses, even if not externally restrained. Internal restraints will take care of that. So this is one complexity that we often not necessarily overlook, but simplify. Another complexity is the inherent non-uniform nature of drying shrinkage. So concrete, as it starts to dry, it will be an evaporation process from the actual concrete towards the environment. This drying is progressive from the surface to inside, and this progression will clearly cause a non-uniform way of contracting for the concrete due to drying, so it will cause internal stresses. These internal stresses are simplified, are accounted for in a simplified manner usually, but they are complex, and these simplified manners may not always be up to the challenge of representing reality. On top of that, we all know that concrete endures creep and relaxation, and so deformations are affected by this phenomena, and these phenomena are also responsible not only for widening cracks in the long run, but also for alleviating the restraint to deformation. So there are counteracting effects sometimes, and they are really complex. They are time dependent. They are cumulative effects throughout time. They depend on the history, and they are the superposition of effects is often not applicable. So again, adding to the complexity. Of course, in the middle of that, the applied loads, which are the classical things that we take into account in engineering for dozens or several decades, but they are there, and they can be really complex as well. And finally, what I've been discussing and saying often, but now I explicitly mention it, the restraint to the imposed deformations in general. So these expansions and contractions due to the early age thermal effects, due to the drying shrinkage that is non-uniform, all this intricate stress development that is happening will have a conditioning factor on how the cracks arise, how the patterns arise. So it's never a single effects blame or cause. So we need to take this into account as a combination. And this combination is really hard to come by. So this is one of the things that we will be addressing when we discuss the goals of our technical committee. So we have a legacy of a previous RILEM technical committee on thermal cracking, as I mentioned before. It was chaired by Eduardo Ferben, a very good friend from Brazil, and co-chaired by me. And this was active between 2013 and 19. It has 43 very active members. We traveled a lot also, much before COVID, really different reality. It seems like a lifetime ago anyway. We travel a lot, we met very many times. We actually introduced for the first time the online meetings idea within RILEM. So when the COVID came, we were already used to have Zoom meetings, for example, or video conference meetings. But in anyway, it's not the same thing. We are really looking forward to start getting out again, and we hope that this will happen soon. To stop speaking about the usual stuff, we made a very interesting book, in my opinion, and even though I'm very suspicious as an editor, but those that find this topic interesting, I think they will find a lot of information. But this book was about thermal cracking, but it was mostly about thermal cracking avoidance. It was not actually much about the actual prediction of the thermal crack width. So this will be the subject matter of the next TC that we are now sharing. However, at the end of this RILEM TC, not only we have created this book, but we also started a very interesting document for the RILEM recommendations on thermomechanical modeling of massive concrete. And this is aimed to provide guidelines to academics and designers on how to choose parameters, on how to choose the type of modeling for simulating these complicated things in mass concrete. This is something that was made independent from the book for the very fact that the book is not supposed to provide opinions. It's proposed to provide a literature review and facts. And the RILEM recommendations are actually a gathering of experts providing their opinion, their recommendation on something. So this was not finished in RILEM 254, but it was finished recently in RILEM in the next TC. So the other thing that I mentioned before was really important also for the networking that we are making, and it still echoes today. So it's Cost Action TU1404. The website is still on, and there was several meetings, there were several training events that I will speak about also. There were several short-term scientific missions. This is actually one of the ways I met Fragolis. He came to Portugal for a short mission as well. And there were many reverberations. And I will speak to you a little bit about this cost action. Its name was, as I mentioned before, towards the next generation of standards for service life of cement-based materials and structures. And we had the objective of trying to contribute to the development of a new generation of guidelines and recommendation. And our methodology was to integrate recent developments in experimental and numerical approaches with particular focus on the performance of concrete since early ages. And we use these very interesting three main sets of tools. So first, mutual validation and benchmarking, both on experimental and numerical side. We try to promote the development of new products together with industry partners. Trust me, this was really hard. And we try to help assisting the drafting of standardization targeted documentation. We made pretty much of this, but much is still to be done, of course. It's interesting to mention the three main focuses of the action. We had the round robin testing, so we made to our best knowledge the biggest round robin testing in the world for concrete. So we shared many tons. I have even a number in one of the next slides about that, and we made very careful protocols on how the testing should be done. And this was a legacy that we are still using it today, and it's a reverberation. So to get repeatable results between different labs, to know we are discussing the same. We made several numerical simulation benchmarking efforts by which different experts from different parts of the world, not only Europe, but also of the world, were trying to simulate the same thing and get somewhere. I'll speak about that as well. And we contributed also a little bit on drafting guidelines and product development, but this was the least successful of the three. All of this was about networking, of course. The The round robin testing was actually, as I said, the largest round robin testing so far as we know. We actually made traveling of 110 tons of material. This has a toll on sustainability, but definitely it was important to learn a lot from it. 43 laboratories were involved, and this document that is already from 2016 was the protocol that we created. It's available online in the website of TU1404. So for laboratory protocols, we really think it's a very good document for concrete and mortar, and even cement-based. And we created several publications. One of those is this one from Springer, but I'll just keep going. It's not the main topic today. Of interest for the topic today is the fact that there was a very strong numerical benchmark activity of groups that were working in a separate manner, and we started to join together our efforts and simulate with different models the same thing. And much of this was also related to the onset of cracking or cracking itself. So we made a benchmarking on concrete structures at early age. We made a benchmarking about the ring test, an experiment that had been made in the round robin program. And we made the benchmarkings on microstructural modeling as well. And we contributed strongly to the benchmarking of the Vercor benchmarking program from Électricité de France, EDF. Interestingly as well, we made some training schools, particularly one in Denmark, for which these three pictures on the left and this one in the bottom belong. There was a very interesting laboratory program for the students of the program also to work together and experiment on advanced testing methods. And then in 2017, also a very interesting doctoral school, actually by our friend at the time named Agnieszka Nopik, and she was the leader of such process. And it was really nice to see the number of people that were there to learn about the modeling. The first one was about experiments and the second about modeling, but also on always on this the similar focus, which was the reinforced concrete structures. So the RILEM TC on an early age and long-term crack width analysis in RC structures came along because of the insufficient materiality of currently existing practices for service limit state design. In fact, we noticed that in many situations, and this is a practice that we are noticing all along, there's an inadequate service life operation, even cracking, when codes are strictly followed. Okay, not always, but there are many situations that are sort of unexplainable, and this goes against the predictability that we want from our codes. Also, we are getting new materials every day. The challenges of sustainability to the world are getting stronger and stronger, and we have to cope with the capacity to bring these new materials to our concrete structures. So then it's, as Fragolis was mentioning before, we have this challenge of supplementary cementitious materials, for example. We need to have new constitutive laws for them. We need to describe their behavior in a very smart way, but we are not able to do it. So how to tackle this challenge? This is really difficult. So we identify these gaps. They are again noticed in the bottom part of the slide, but we started this TC and we gathered a lot of people interested. So I now invite Fragolis. I will go to the next slide and you will take over the rest of the presentation. Thank you.
Thanks, Miguel. Right, so thanks very much, Miguel, for this introductory part of our presentation. Now, my part will mostly focus on the specifics of the RILEM committee, RILEM TC 87 CCS. So the committee started in December 2019 with a target duration of 5 to 7 years. We initially started with 25 members, but month by month we were growing, and we currently have almost 60 confirmed members, and this demonstrates the popularity of the subject. And we have attracted engineers and practitioners and researchers from industrial institutions and also from the academic world. So this is a great collaboration hub for us, and on top of the efforts that we are having to improve our knowledge on crack control. The main target deliverables of the TC were the recommendations on thermal-chemical mechanical modeling of massive concrete structures, and ultimately a book on an interdisciplinary approach to early age and long-term crack width analysis in reinforced concrete structures, which aims to combine the best materials knowledge with the best structural design knowledge in order to achieve the most optimum results and to promote collaboration between different disciplines. Now we'll move to the next slide. So the first outcome of the committee was the publication of the recommendations document in Materials and Structures. That's RILEM's flagship journal, and this was completed in 2021. It was a great milestone for this to see, because to our knowledge, there hasn't been a recommendations document as official as a RILEM recommendations document, merely and solely on numerical aspects, and particularly for thermochemical mechanical modeling of massive concrete structures, but it could be for any concrete structure in particular. We many times come across challenges that we don't know how to overcome, which model to use, what coefficient of thermal expansion to use, what should I do with the reinforcement, what is the thermal conductivity of this and that, and what is the creep model I should be considering, and so on. So because we faced those problems during our development as crack control experts, we always like to come across a document that will serve exactly that purpose, give us guidance on these aspects, and this is what this document is doing. So I'm sure many of you will find it very useful, and it's also, I believe, it is open access. And further on, sorry, I have some delay in changing the slides. Okay, so in terms of meetings, we're an online-based committee given the current circumstances with COVID-19. That doesn't mean that the productivity of the committee has dropped. Actually, it is very good. It is the social component that we miss. But we have done already 5 meetings. And even this year, we were able to organize a dedicated conference in the committee during the RILEM Spring Convention, where we have a great participation of people from academia and the industry expressing their views and their findings research-wise and design-wise on early age and long-term crack width control in reinforced concrete structures. The proceedings of the conference are available through Springer and can be accessed. So that was another milestone for the technical committee. That was also very useful for us to perpetuate the pace we were having, and also shape the future of the committee research-wise, and what we should be targeted on. So going into the specifics of the RILEM TC CCS. We essentially have now certain work packages which will be translated into book chapters, and all of them look at the distinct themes that are associated with cracking and crack control. I will go through them one by one as fast as I can, given the time limitations. So initially, we start with an introduction and what is the cause of cracking and some terminology. Then we talk about experimental results in the laboratory. Then we move on for in situ evidence of cracking. We review the code-based approaches. We review the non-code-based approaches. We talk about numerical simulations at multi-scales. And we challenge and critique the cracking performance requirements in different parts of the world. We review the materials techniques that can be employed to improve cracking performance and cracking resistance. And we also explore the integrated measures on the supply chain towards better cracking performance overall. So I will go one by one and try to describe the scope of each work package. and perhaps accentuate the importance of each one of them. So in terms of relevance and phenomenology, which is the first two work packages of the RILEM TC CCS, we do know, as Miguel said previously, that cracking occurs due to several reasons. But in this case, we are particularly interested to restrained imposed deformations, which is relevant to SLS cracking. This can be due to heat of hydration, and long-term temperature changes, drying and touching, shrinkage and creep, and also the effects of restraints themselves. These are often, or most of the time, superimposed with loads. So we have load-induced cracking also. And the particular focus of the TC is how to calculate and how to control the crack widths on site. So we want and try to combine these two effects that traditionally have been treated differently and separately, and throughout the life of the concrete since the beginning, since casting. So the time scales are from early ages till the end of service life, let's say. And that encompasses all the different mechanisms and phenomena associated with cracking. Now, at this point, we are excluding several phenomena that lead to cracking, particular loading situations related to fire and cryogenic temperatures, extreme loading due to earthquake or impact and blasting and fatigue, any deleterious swelling reactions like ASR and delayed entry guide formation or rebar corrosion, and cracking that occurs before setting or at the time of setting, while concrete is still probably a little bit more fluid, like plastic shrinkage, plastic settlement, and crazing. And this is because there are fundamental differences between the cracking mechanisms and the drivers for cracking between these phenomena, between the imposed deformations and the load induced and the typical load induced and the aforementioned phenomena. So on laboratory scale, there are a lot to investigate, and there are several techniques and methods that can be employed in the lab to obtain information regarding the cracking characteristics of concrete, restrained cracking characteristics of concrete. So the aim of this work package is to actually review which experimental technique provide which information which are relevant to cracking, what are the limitations, and which one to employ given the specifics of a particular situation, time, cost, possibly availability of equipment, ease of construction, and so on, and what we should be expecting out of these experimental techniques. We also cover how to actually measure cracking with what sort of technique. Is it a surface mounted reducer? Can we employ wave propagation methods or even microscopy, tomography, and CT scan, and so on? And these are all relevant to cracking and crack propagation and crack depth. And we also cover tests due to applied load, the typical direct tension tests or typical bending tests or even cyclic loading. And although I mentioned that we don't explicitly account for the cracking due to durability mechanisms and due to chemical attack or the rebar corrosion, for the test component, we thought it would be particularly useful to because we cannot easily calculate and control cracking due to these mechanisms, at least we can propose or look further into techniques to measure cracking due to these causes. Further on, the next work package is on in situ evidence repository, where we are attempting to compile evidence of cracking in several different types of structures, including restrained walls like tunnels, containment buildings, basements, and so on, foundation slabs. We come across them in warehouse slabs and other massive type base slabs, suspended slabs, and any other massive concrete element. And we do really cover a big breadth of types of structures, bridges, tunnels, buildings, nuclear structures, hydraulic structures requiring leak tightness, and so on. But the fundamental requirement for an entry to this work package is that for each case, we should have a comprehensive set of data with respect to cracking and what caused the cracking. So we have measured temperature histories, strain or even stress histories, crack width measurements, what the casting and construction methodology when cracking was first noticed, and the concrete mix characteristics. And also we are attempting to cover evidence for touching and shielding as well. And ultimately, the main aim of this work package is to create a comprehensive database of evidence of cracking in actual structures where actual people designed them, and we have data about it. So we can back calculate what went wrong, or we can even use the results to validate our models or even our experiments. Okay, further on, we're looking at a quite important also aspect of this committee is how different regions in the world deal with the problem of crack control. We do know that there is no unified method to control cracks in concrete, at least not due to imposed deformation. And earlier this year or the year before, we actually conducted a study within the committee, with collaboration with the committee and ARP, where we found that there are huge differences, discrepancies between the rebar amounts required to control a certain crack width for a certain structural arrangement. So as an example, if you have an edge restrained wall, how much reinforcement would you need to to control the crack width to 0.3 millimeters, which is the typical crack width required by most codes. And we investigated Eurocode 2, different Syria guidances, Australian standards, and German specific guidelines. And you can see the difference that for a given crack width, there are massive differences in estimates for rebar reinforcement required. So this brings us in an uncomfortable position of not being able to reliably assess either which code is correct or more accurate or more reliable, and to we're not in the position to understand why these codes behave so much differently. So this work package aims to review all the different available codes to us with respect to crack control, but also comprehend in depth the reasons for having discrepancies between the different codes. So at the moment, we have collected information regarding codes dealing with crack control from different countries around the world. We have great participations from actually all continents, I would say, and this is still growing. This world map is currently being updated. We have entries for North American standards. We have entries for Australian standards. So the list is really growing, and I think it will be of a very meaningful output once we manage to get all the specifics of the code-based approaches. But apart from the code-based approaches, there are certain non-standardized approaches, analytical and semi-analytical, that can be used to calculate crack widths and control cracks in concrete. And these may be a little bit more advanced than the traditional ones, but there's still a very much enough merit on looking at them more closely and comparing how these methods perform against the code-based approaches and against either experimental results or cases where cracking occurred, as I mentioned previously in the slide for in situ evidence repository. So all these evidence that we have for cracking will be used in conjunction with these techniques to try and assess their differences and their applicability to crack control. So we have also a lot of participants in this work package as well, from different, mainly European country, predominantly, I would say, and ultimately will be compared with accuracy of codified models. Further on, we the next work package is 7, and this is a topic where it hasn't received much attention, I would say, on the wider engineering community with respect to crack control. And this is because most of the models that are micro scale, let's say, or many are models of modeling something of bigger scale, but micro and meso scale are still very useful and very provide fundamental knowledge with respect to concrete property development, and can be used also in conjunction with macro scale to feed, let's say, the model. So upscaling the model from micro scale to macro scale can actually give us a very good view of how properties develop within concrete, what is happening with micro cracking. But also in this work package, we will be reviewing the numerical methods that can be used at the micro and major scale, and establish a numerical benchmark, which will be based on certain cases, will be modeled by the participants, and then we will reach conclusions as to the peculiarities, which are the peculiarities of each different model. And after the micro and meso scale, we go to macro scale or finite element-based simulations. These are the most frequently employed types of simulation to model cracking, but still we know that there are very complex processes associated with modeling cracking, especially at the multi-physics level. So we combine different physics, thermal, chemical, hydral, to try and predict the behavior of concrete, but at the same time we want to actually predict cracking and see whether cracks can be controlled in numerical models, and what precautions should be made. And this puts an emphasis on how to model the actual mechanisms, like constitutive modeling, hydration, drain, touching, shrinkage, and creep, and also how to model cracking more reliably or specifically for a case. Again, we will set up a numerical benchmarking where different modeling approaches will be compared, and this is based on past experience. This is very meaningful, not only to improve models, but also to improve our interpretation of the modeling results. Further on, we went on to challenge either of the current standards, but first review actually the standards and what the cracking performance requirements are for predominantly aesthetic durability and leak tightness. We review such requirements, and we assess the relevance of cracking to the above requirements. Sometimes cracks are aesthetically, crack width limits are aesthetically driven, and some other times, even if they're not, they become because the unacceptable cracking occurs, like in this case in the Holocaust Memorial in Berlin, in these very well-known blocks. On other occasions, we know that some structures have to be leak tight, watertight, like hydraulic structures, but we do get cracks either wide or less wide that are of less concern, but still of concern occurring, like the one that occurred in this concrete spillway. Another topic that is being addressed and is very relevant to how we specify crack width limits, why we specify them, and whether it makes sense to specify them with relevance to durability, is how cracks affect actually durability. Do they promote reinforcement corrosion? Do they accelerate corrosion propagation in the reinforcement? What happens in a carbonation-rich environment? What happens in de-icing-rich environment and marine environments? And all these peculiarities are reviewed. We know that these topics are still debatable, but we are hoping to shed some further light on it. And we compare what are the code-based performance requirements globally. I mean, at least for the guidance documents that we have in our hand and we're able to collect, and we will see how different regions deal with performance requirements for cracking in particular. Further on, we are reviewing and providing suggestions regarding materials techniques toward improving the cracking performance. And this is referring to either self-healing, or autogenous healing, or non-autogenous healing based on bacteria, and how efficient that is, and what methods are there to conduct these, to apply this technique. We have a section where we're discussing the effects of fibers on improving cracking performance, and how different fibers affect the cracking performance of the concrete, and whether we can use any codified or an analytical model to actually calculate the contribution of each fiber of each fiber type towards crack control. But on top of that, sorry about the duplication of bullets, we are looking into the efficacy of waterproofing admixtures in closing cracks and healing the cracks, and also further internal curing methods like employing super absorbent polymers, shrinkage reduced admixtures, and lightweight aggregates. And finally, we give an insight on the different repair methods and where they should be applied, and what is their efficiency towards cracking performance and improving the leak tightness, for example, or a crack bridge and providing load transfer through the cracks. Finally, the last work package is on integrating measures on the supply chain towards better performance, and this is really to identify what the bottlenecks are in the supply chain. Review some formal guidance that has been developed through the past years that recommends the integration of material specialists in the design construction phase, and will provide some example of integrated design of mixture composition together with structural behavior since conception, and we will provide several examples that this combination during the early stages of the project resulted in a much more favorable outcome with respect to cracking and serviceability, and point in the directions of the integration, proposing workflows integrated with a new BIM processes following the corresponding ISO. So hopefully I didn't overrun much. And as a closing remark, both me and Miguel would like to share our final thoughts. We'd like to say that much is known, but much is yet to be learned. And every day for us is a new learning experience. So this is a call for actions. Action, please join us in RILEM and let us learn together and progress the knowledge and cracking further on. Thank you.
Okay, thank you. And I guess that wraps it. Thank you.
Thank you.